All right, welcome back, everyone. So let's dive in right away to our next presentation. Our next speaker is going to be Golnoosh Farnadi, who's a core Mila member and assistant professor in the Department of Decision Science at HEC Montréal, and an adjunct professor at the Department of Computer Science and Operations Research at University of Montreal. She develops novel machine learning and AI models to tackle fairness and ethics in AI. And her recent work is mainly focused on addressing bias and algorithmic discrimination in decision-making models. So today she's going to tackle the topic of algorithmic fairness, a pathway to developing responsible AI systems. Golnoosh, thanks for joining us virtually. The floor is yours.
Thank you so much for having me. And I'm sorry about my voice, and I'm sorry that I cannot be there. I'm sick and I'm actually in San Francisco. Also kind of to correct it, because from tomorrow I will start at McGill University, so my affiliation would change. So this is kind of the affiliation that you are seeing also on the slides. So without further ado, I will go through the slides. I'm actually working at the intersection of algorithmic fairness and privacy, but for this particular talk, I will mainly focusing on algorithmic fairness. I will give you kind of like crash course of like the field, and also like my work in this direction. So I will start with this question of like why we should care about algorithmic fairness. What is the importance of algorithmic fairness? But before answering this question, it's a kind of like disclaimer of like what I'm including in this talk is just the technical approaches to mitigating algorithmic discrimination. But there are other approaches that are not included in this talk, like this kind of like journalism that are investigating, or auditors or policymakers or advocacy groups or the community organizations around this topic. Often I'm starting this question from the audience, like who already know what is algorithmic fairness and who they have no clue what is algorithmic fairness, because I cannot see the audience. I will assume like some of you know, some of you don't. So I'm hoping that at the end of this presentation, there is something that you learn from it. So why we care about algorithmic fairness? We are living this era that like AI is going to be staying. So in different industry, like this is kind of like the pot I got from the Accenture research that they published recently, that is showing like how much AI actually helped the growth of different industry. Kind of like some of the industry are early adopters to AI and some of them are late adopters. But like you can check it here, and like they're kind of like the growth of like using AI is significant in all industry. What does that mean is that like AI is going to be used in various applications, including the applications that have the influence on people's lives. So currently AI is used in like applications that kind of like show you the job advertisement, deciding who gets a job, who goes to the jail, who receive loans from the bank, and who get diagnosis and receive healthcare. And you can kind of understand that all these applications are very sensitive. So my goal is kind of like to answer this question, whether these automated decision-making systems that we are using are fair or not. Unfortunately, the answer to this question, and it's realistic, we have scenarios around the world about like this is not the case. So the current state of the AI, if you're not changing the way that we are using it, is going to create harms. Here, I just included a couple of scenarios, couple of like use cases that went viral. So you may already seen these. And I also included the categories of algorithmic harms. It's not an extensive list of harms. And also I want to kind of emphasize of the harms that are not kind of exclusive, so you can have different harms appearing in one system. So here you can see an example of like the Amazon recruitment tool. I'm not sure if you see my mouse on the screen. Can you see it?
Yeah, we can go.
Yes, okay, awesome. So here, and this example is in 2015, Amazon launched an AI recruitment tool that was favoring men for technical and highly paid job. They couldn't fix the problem, so they actually canceled this service. And the problem they were saying is that like they were training the model based on their own data from the hiring at Amazon, and because like most of the people at Amazon working are men, or like it's a kind of technical jobs for men and they are white, So that's why they were favoring like technical jobs for men and highly paid jobs for men. Here you can see the Compass, which is the risk assessment tool that is used across courts in the US. And ProPublica in 2017 published this article that's showing that the risks that are for Black people are higher than the white people. And what does that mean? At courts, when they are seeing the higher score, they may actually sentence people to jail. So this kind of like risk that you are seeing is different for men and women, or from the kind of like different race groups. We call them allocation harm, like the harm towards different people. You could also have a quality of service harm. So you may be familiar with this gender shade study that Joy Bolvini, which was at the time MIT researcher who kind of like studied different facial recognition technology. She realized that like these technologies cannot recognize her face. So that's kind of like in this picture, you're seeing that she's having this white mask, because like only with the white mask and this face recognition technology can recognize her face. And then we run this study that it gets very famous, which called Gender Shades, that she showed that like this is not just about the characteristics of her face. Actually, sorry, these face recognition technologies are doing a poor job for the darker shade color skins, specifically women. It's showing the quality of service harm. Like the quality of service is actually different when you are in different populations. And it's also true, for example, for virtual machines, that like it shows in different studies that are making women sick. You could also have a stereotyping harm. So in predictive policing, specifically in the US, there are multiple studies showing that there is kind of like a stereotyping harm towards Black communities. So there are studies showing that like the predictive policing is used to kind of like predict which areas the police should go to investigate. And that's kind of a study that you're showing here, that like either they are stopping the cars that like Black people are driving, or they're going to the neighborhoods that the Black people are living, while there are investigators showing that like it's not because the crime rate is higher, it's just the stereotyping harm. We're also seeing a stereotyping harms in different NLP applications, for example, in translation, that we can see that, for example, there is association with the word woman and nurse, or man and doctor. We also have denigration harm that is almost always rooted to cultural issues or historical issues. So we had this horrible example of like mislabeling images of Black women as gorillas, or you may are familiar with the chatbot Tay for kind of like learning to have a hate speech towards people. And then we also have over or underrepresentation harm, that, for example, if you're searching to get the results, for example, if you're searching for CEOs, often the results are kind of like overrepresenting men, or if you're searching for basketball players, it's kind of overrepresenting Black communities. So harm is one reason that we should care about algorithmic discrimination. But there's also another reason that we need to think about it, and that's laws against discrimination. So in different countries, and you can see like different snippet of like the legal documents that I put on this slide from the US, Canada, China, Africa, Europe, or India, that we do have laws against discrimination. So if you look at this part about like the US, is very similar to Canada and Europe as well, that we have regulated domains. So credit, education, employment, housing are regulated domains, and we have legally recognized protected classes. They refer to it as sensitive attributes during this talk, that is including race, color, sex, religion, national origin, etc., etc. And what does that mean is that when you are applying for a credit card, you should not be discriminated based on your race or sex. So I gave you two reasons of like why we should definitely care about algorithmic fairness. But then the question is like how we can define fairness in machine learning. First of all, fairness is a socio-technical challenge. So the part that I'm including here is just like a technical aspect of it. Although the fairness should be included in the discussion with social scientists, lawyers, because of the legal aspect to it, as well as computer scientists. Also, many aspects of fairness are not going to be captured in mathematical notation. So kind of like a disclaimer of like, I'm showing the mathematical notations here. but it's not covered all aspects of fairness. To give you a more understanding of like different mathematical notations, I have running example throughout this talk. So assuming that there is a bank that they want to give a loan to people, and we know that like loan is protected by law. So we have the loan application that there are a couple of non-sensitive attributes. So for example, their saving account, how much money they have, what is their education level, what is their job title. And then we also have a sensitive attribute. So for the simplicity, I'm thinking that there is only one sensitive attribute here, and that's the gender. And I'm also for simplicity assuming that gender is binary. Of course, gender is not binary, but that's just for sake of simplicity here. We are assuming here that like it's just a simple binary classification task. So the task is just giving like kind of approving the loan or not. And it's a supervised learning task, meaning that we do have the actual label Y, and then the prediction of the model is going to be the Y hat. So how we define fairness in machine learning? So there are two categories of fairness notions in general. So one, and both of these categories are kind of inspired from the legal documents. The first is individual fairness category, which is trying to measure the impact of discrimination at the level of individuals. This notion first defined by Cynthia Dwork in 2012, and she actually defined it based on Lipschitz condition. So if you're not familiar with Lipschitz condition, is that she defined that like two similar individuals should be treated similarly with the model, which means that if we have X and Y as two individuals, and the space of the individuals, there is this distance D that we can define between these two individuals. The outcome of the model, so mx and my, should be bounded by the distance of the individual in the inputted space, right? So Lipschitz condition is just saying that like this outcome should be similar to the level of the similarity individuals in the inputted space. But fairness is very subjective. It should define it based on the context. So for instance, for the loan approval, we can define this individual fairness notion as similar applicants with exactly similar application that only their gender differs. So like they have the exact saving account, exact education, exact jobs, they should receive the similar decision from the model, right? So if it's going to be approval or not approval, it should be exactly the same. And that notion is in the literature known as causal discrimination notion. And this is kind of like a notion that we used in our work, and I will later on discuss it with my student Kiarash and our collaborator Aishwarya. The same notion of individual fairness can be defined very differently when we are kind of thinking about another context. And here I'm referring to kidney exchange program. So if you're not familiar with kidney exchange program, it's a program that's running in different countries, including Canada, for the people who are in need of a kidney transplant. So they're actually entering this pool of people that like the people coming with a donor that is not compatible with them in order to find a compatible donor from another pair. My student actually after me giving a talk to give you more details of kidney exchange programs. But like how we define individual fairness here is that we realize that like the chance of receiving a kidney is not similar for all the individuals. So just being in the pool of kidney exchange program doesn't necessarily guarantee that you are going to receive a kidney. So here in this work, we define this kind of notion of individual fairness as if two people are entering this pool as kind of like they are similar patients, they should have similar chances of receiving kidney transplants. And finally, I have some works at recommender system and information retrieval, and we kind of define individual fairness as fairness with respect to exposure bias. So in information retrieval systems, it is very important kind of like in the kind of search results where the results are appearing. So kind of in the ranking of the results are coming, the first and seconds are very, very different. So here we are kind of studying like how we can have this kind of like privacy and also kind of fairness approaches to ranking that the items that are kind of like similar in terms of the relevancy to the query, they should have a similar exposure as well. We also define the similarity for the recommender systems, and specifically we look at the music recommender systems. We're showing that like in recommender system, we have popularity bias. Like most of the times the popular items are more often to be recommended. So we tackle this problem as an individual fairness thing, that if two items, and here we are talking about the music items, if they have exactly or are very similar music features or very similar quality, they should have the same chance of being recommended for the playlist a continuation task. So here I just show you 3 examples of like individual fairness, and you can see that in 3 different scenarios, the way that I kind of like define individual fairness is very different. And this is the scenario. So if people are asking like how I should use individual fairness, it's very, very context dependent. So you should look into your application to have a better understanding how to define it. But individual fairness is just one category of fairness notion. The other category is also group fairness notion. So group fairness notion, they're trying to measure the impact of discrimination on the group of individuals. Often, this group of individuals are defined based on the sensitive attributes. So for example, female versus male group. So the probability of receiving the positive loan approval, for example, in our application, we wanted to make sure that it is similar among female and male applicants. Here I added 3 most popular group fairness notions that people are using in literature. The first one is demographic parity. Demographic parity is actually a notion that is used in the legal documents in the US, and many people knowing at 80-20 rule. And what does it say is that the probability of like advantage, and here, for example, getting the loan should be similar if you are belonging to the female group or male group. So this is a nice notion, but it has several problems. The first problem is that it only cares about like the average kind of like a popularity of acceptance. And it's not including any aspect of the quality of those applicants. So the applicants are not qualified to receiving a loan. For this scenario, for this notion of fairness, they may receive the loan. To address this issue, we have these 2 other notion of fairness. So equal opportunity is actually focusing on this kind of like the same notion. So we are trying to remove the dependency of the sensitive attribute from the positive outcome. But here we are also including, so in this kind of like supervised learning task, the label. And by including the label, we are kind of trying to make sure that the true positive rate is kind of like equivalent across different groups, right? So kind of considering that like they are having the qualified applications when they are receiving a loan. But the problem with equal opportunity is that we are only focusing on the positive outcome and the true positive rate, right? So what would happen if like you are giving the loan to the people that they are not qualified? So what would happen in the false positive rates? So equal odds actually kind of focusing on that aspect that like no matter the label, so whether it was a positive or negative, right? And you are giving the loan, you want to kind of like equalize even the harm of like giving the loan to someone that were not qualified. So you want to make sure that like across, for example, female and male group, the one that are not even qualified to receive a loan and they are receiving a loan is kind of like equivalent. One thing about the fairness notion, I only included some notion of fairness here, a statistical notion of fairness, but we do have impossibility theorem of fairness. So you may think of like the last slide, I show you 3 notions and they may all make sense. But unfortunately, you cannot really satisfy all 3 at the same time. So you have to actually select one of those notions in your applications because this is impossible. And we have different papers showing like this kind of impossibility theorem of fairness notions, that at the end of the day, you need to kind of like select one fairness notion. And we already know that one fairness notion cannot simultaneously satisfy all metrics. Also, in terms of individual fairness and group fairness notions, we also do have papers showing that you cannot really satisfy both at the same time. And here is a kind of like silly examples of like, if like we are thinking of like all females should receive the same decision, all male are receiving the same decision, that's a notion of individual fairness, but it's not necessarily satisfying the other group fairness notion that we want to make sure that the probability of receiving a positive loan is similar across different groups. The other aspect that I want to also consider here is the intersectional fairness. So here I started with the example of like we only have one sensitive attributes, but often we do have multiple sensitive attributes. So individuals are often defining based on this kind of like overlapping dimensions, including gender, sexual orientation, age, and disability. There are protected attributes. So one way that people are kind of like considering it is just like group fairness with respect to multiple of these dimensions. So gender shade study is actually kind of showing that if you're looking at the darker shade color women, you can see the huge kind of like differences in terms of the performance compared to other subpopulation. But if you're just considering women versus men or black versus white, you're not seeing that much of a difference. But you should be careful about this because when you are considering many dimensions, you're getting closer and closer to kind of like getting to a single individuals. And obviously you don't want to kind of like make the decision equivalent for all individuals in your system. So there is kind of a trade-off of like how many of these sensitive attributes you want to include it when you are kind of creating these groups. And maybe you want to kind of like go towards individual fairness notion that you are actually defining how to go for the similarity between individuals instead of like grouping them based on multiple sensitive attributes. Another thing that I want to mention is that like maybe you also want to treat them differently. So in our recent study on vaccination strategy, we see that for the COVID, the aftermath shows that like based on the mobility of the people are from certain racial groups or income level, they were more at the risk of getting the disease. So we're kind of coming up with this method of like how we can make it fair based on the mobility. But then we consider that, for example, race should be similar. So the chance of, for example, getting the infection kind of like should be similar across different race. But we cannot really treat it similarly based on age because age, there is a risk factor there, right? So you cannot say that all ages should be similar because for older generations, obviously, the risk is much higher. So kind of like we have to include this kind of like that there's differences of different attributes and you cannot just simply combining them. For the sake of complexity, I also kind of including this dimension of causal notion of fairness. So I included this kind of a statistical notion of fairness, but causal notion of fairness are kind of like the other dimension that is also included in legal documents that we need to find the causal aspect of discrimination. And the problem with the causal notion of fairness is that often you require to have the causal model of the word. So often we refer to it as the circular causal model. And if you do have it, then we can kind of like define fairness notion. And often it is based on a path from the sensitive attribute to the decision. So I cover like how we can kind of define fairness notions. But now the question is, okay, so we have the fairness notion, we selected the fairness notion, but how we can actually use this fairness notion in machine learning? Algorithmic fairness is highly dependent on the fairness notion, obviously, and changing the fairness notion actually going to change your mitigation approach. And also, you should not really consider fairness as an aftermath problem, right? So when you're kind of building the whole pipeline and kind of like just the evaluation based on fairness. So here I'm guys showing like how you can actually consider fairness when you are designing a model. So in order to understand it, here I actually included a very simple pipeline. So the pipeline of machine learning often is that there is an input, like a data, and there is a model that kind of like learning from that input, and then we have the outcome. So bias or this kind of like discrimination that like we're talking about is actually appearing throughout this life cycle. So we can have data which is unbalanced. So in terms of, for example, Amazon recruitment tool, most of the data were coming from the white male. We can have historical discrimination. So for example, in predictive policing, we had historical discrimination that like the police kind of often kind of like consider Black people as criminals, or we have encoded of the protected attributes in the data itself. So even kind of like removing a sensitive attribute is not necessarily solving the problem because of all the kind of like relationship between the sensitive and non-sensitive attributes. We also have issues in the model and the design of the model itself. So many people are actually arguing in this kind of algorithmic fairness literature, or kind of like there are debates about it, that like all the issues of algorithmic fairness are data problems. But I want to argue it's not the case. So it's kind of like with the way that we are designing the models, we are designing with the unfair objectives. In the recommender system, like the popularity bias is kind of coming off the way that the model is working in a way that they're creating this popularity bias, right? And often like the designer of the model, they are kind of like using this model as a black box, so they don't have this kind of like knowledge of like the algorithmic design, so they cannot really change the loss function, etc., to fix the problem. And then we also have the biases of the outcome, because like often like we cannot really understand, like if you're using, for example, deep learning models, we don't have a better understanding of like how the model is getting this decision based on the inputs, right? And like when we don't have even user feedback, sometimes we are creating this kind of feedback loop in the systems that like when we are creating the outcome and the model actually using that outcome as an input to the model, kind of creating the feedback loop. So depending where in this pipeline we are trying to address the bias, we have different techniques that we are referring to them as pre-processing, in-processing, or post-processing techniques. So I will give you some overview of like each one of these categories. Of course, it's not kind of like the complete list. The first one is kind of like how we can address the fairness in pre-processing by just focusing on the data and the data debiasing. So assuming that this is our data for this kind of loan application scenario, and we have a couple of, for example, positive decision and negative decision, and you can see that the data itself is biased because like most of the male are getting the positive decision while females are receiving the negative decision. So one thing that people are talking about is that we can kind of massaging the data set itself. So one way is that we can kind of learning kind of like a similarity, kind of a classifier that kind of recognizing that if, for example, these two individuals are similar, but the labels are different, how we can kind of like favor the disadvantaged group and kind of like changing their labels. So for example, here we are seeing these two individuals are very similar to each other. Then we can kind of like make this individual that has a negative label to have a positive label now, and this individual that has the positive label to have a negative label in order to have a more balanced data set to begin with. Many people are arguing that we should not really change the labels of the data set. So can we do other things? Yes. So there is another approach that like considering the reweighting of the data points. So here, for example, to make sure that the classifier kind of like treats the data, kind of like seeing a balanced data set, they're kind of creating the weights for the data points. So kind of increasing the weights of these data points in the negative case for males and this data point for the positive case for female in order to have the more balanced data set. Although we should be careful about this kind of reweighting techniques because this kind of like not kind of increasing a diversity of female or male applicants that we are seeing actually here. And there's another simple technique is just sampling, right? So we can actually sample one female and one male for positive, one female and one male for negative, but it has a similar issue of reweighting because you are kind of like even reducing the space that you had, for example, to learn from the male applicants here even to have a better model. More recent kind of like approaches are they're talking about that like maybe we should actually learn this kind of distribution. So maybe we can kind of go towards this kind of data generative models and learn the distribution of the female and male applicants and generate synthetic data points in order to have a balanced data set. So there are kind of like techniques going from the, for example, generative adversarial networks to variational autoencoders in order to learn these kind of distributions. Another variations of the techniques, they are focusing on fair representation learning models. So if you're not familiar with representation learning, is just like when we have this space of individuals, we want to kind of like go to the latent space, like for example, Z from the input space, that like this space is actually useful for us to have a better kind of like model for the outcome, right? So often the goal of representation learning is preserving the performance of like based on the utility, so downstream tasks, but also we want to make sure that when we are going to this kind of latent space, it is also kind of like preserving the quality of the input data, right? So we should able to go from X to Z and kind of like go back from Z to X. So we have the reconstruction loss for that aspect. When we are considering the fairness of representation learning, we are kind of adding another goal in the representation learning. So in addition to this kind of like the performance, we want to also make sure that, for example, with respect to group fairness, the distribution of the female and male with respect to all these dimensions in kind of latent space are kind of similar to each other. There's also another aspect that when we are talking about group fairness, often we want to remove the dependency of the sensitive attribute from the decision. So they try to simply actually debiasing the latent space. So by kind of removing the sensitive attributes from that latent space, that kind of like have a neutral representation of the data. In terms of individual fairness, we also kind of like trying to do similarly. So if you remember the notion of individual fairness, we were saying that we want to make sure that the similar individual having the similar outcome, and we can also think of it like in representation learning. We want to make sure that like the dimension in the representation learning in this kind of like latent space is also kind of like similar, so kind of like satisfying this Lipschitz condition. Individual fairness for representation learning has many applications actually in finance, in rankings, and in healthcare. And here I just include one of the examples from our work on like how individual fairness, as I said, for the task of popularity bias can actually help us. So here it's kind of like this syntactic scenario that if you have two kind of like music art items, that one is a very popular item, and we create exactly the same item, but it's not popular, so it's only appearing in one playlist. And when we are learning this kind of representations, we show that like this graph neural network representation learning is actually kind of including this kind of popularity bias. So then the distance between the individuals that this kind of like items are actually increasing. And we are approached that like we are removing this kind of like biases, we are actually similarly getting the same representation for these two items, kind of removing this popularity bias. So I kind of cover some techniques for data debiasing or pre-processing techniques, but I also want to include like what we can do with respect to our models. So in machine learning models or AI, we're often looking at the optimization problem. So supervised learning task that I mentioned here is expressed as an optimization problem that we are trying to often minimize a certain metric. For example, we are trying to minimize error, or we are trying to maximize the accuracy. So the goal of this optimization that we are solving is that there is this function form. For example, deep learning is a function, and we are trying to learn the best parameters for that model that minimizing this kind of metric. So fairness can be we can think of fairness as a kind of like another property. So here we have this metric as error. So we want to also include fairness as another kind of like metric to this optimization problem. But we should be careful here because not all optimization problems are the same. So we have kind of like the space of different machine learning and AI model. Each one of them, they have different properties. Some of them are easy to solve. For example, there are convex optimization problem, or there are linear models, but some of them are very hard. For example, deep learning models that like there is no exact solver for it, but we do have kind of like approximate solvers for them that behave really well. But fairness can actually change all these properties. So there are three actually ways that people are considering like adding fairness to this optimization problem. The first is that like considering the fairness as a constraint to this optimization problem. The way that like a constraint optimization problem is useful for fairness notion is that first of all, you can actually provide some sort of guarantees that like if you have this kind of like differences of, for example, female versus male group with respect to the accuracy or with respect to the favor decision, then we can include them as a constraint, and it's going to be very interpretable, like why kind of like this model is going to be more fair than other models. But constraint optimization problems are very hard to solve. So here I just put an example of one of my recent work of like how by adding this kind of fairness constraint, like the whole problem is changing. So here we started with naive-Bayes classifier. So naive-Bayes classifier is a very simple model, but the optimization problem is actually convex optimization problem, and we can find kind of like solve in a closed form. So here we started with this fairness notion that we want to make sure that probability of the decision, no matter is positive or negative, is actually independent of the sensitive attribute. But here we actually included this intersectionality of fairness. So we included like multiple attributes in our system, and then we wanted to add it as a constraint to this optimization problem. The problem was that when we're adding this constraint to the optimization problem, first of all, the constraint were not convex, right? Because you can see this condition, and this is not a linear form. So the first question was like, how we can actually solve this optimization problem? What kind of solver we actually can use to solve this optimization problem? So for this, we actually try to kind of like approximate this kind of like formulation and solve it with a signomial program. It still is a local solver, it's a kind of approximation, but still we can solve this optimization problem. But then there is another problem. When we are considering intersectionality of fairness, then we are going to have exponentially many constraints that we have to satisfy, because we are considering all the combinations of a sensitive and non-sensitive attribute actually here. So in order to address that, we define this kind of cutting plane idea that like we were trying to select the constraint and add a constraint to the optimization problem and solving it with kind of like a small set of constraint, and then kind of like this is doable to do, but like then we have to iteratively doing it to kind of like solve that optimization problem. And at each iteration, we kind of like checking whether there is unsatisfied constraint in order to add them at the next iteration. But then again, the question is like how we can select this constraint, how we can actually order all the constraints in order to include them at each iteration. So we also kind of coming up with the way of like selecting the constraints. So we can start with the most violated constraint or the most probable constraint, or something at the intersection based on KL divergence of like the constraint that we want to include is mostly violated, and also there are probable to be included. And we show that with very few iteration, we can actually kind of like solve this problem. And coming up with the Farnadi based classifier, we also kind of like compare the performance with other works, and we show that first of all, like our work is much better than the kind of like existing work on Farnadi based classifier. And also like because it's the likelihood kind of like the goal is kind of maximizing. So in terms of a loss function, we are kind of paying some price, but kind of considering the scenario that we are removing all the dependency of the sensitive attribute from the data, the performance is much better. So one of the reasons that like kind of considering fairness at the model aspect or in processing aspect is that you can actually get the better performance than just removing the sensitive attributes from the data. Another aspect is that like this kind of removing the sensitive attribute from the data, kind of like we kind of use the state-of-the-art approaches for doing it. And we show that even when we are considering 0.99% removal of sensitive attribute dependencies, still we may have kind of like thousands of this kind of like unsatisfied constraint in the model. So it's not going to be enough to just focusing on the data. So I only consider, like I only mention about constraint optimization, but something that is more common to use is adding it as a regularizer. So adding as a regularizer mean here that we are adding the fairness here. So for example, you are trying to minimize error, and then you're adding, for example, the difference between the error of the female and male applicants should also be similar, right? So we are kind of like minimizing error and also the distance between the error of the female and male group. Here, the regularizer is, there's something nice about it is that you can also add a coefficient to have a trade-off between like kind of the utility and fairness. But while it might be sounds easy for group fairness notion, it's not necessarily easy for individual fairness notions, because you have to compare with the pair of all individuals. So here in this work, we actually try to kind of work with individual fairness notions and how we can add it as a regularizer. And we started with this motivation example from the Apple. I'm not sure if you heard about it, that Apple actually launched this kind of credit card. And then it turned out that it had gender discrimination, because there was a couple that like everything about their profile was exactly the same except their gender. And one of them kind of like received kind of like the credit card and the other got rejected. And then they tweet about it and it went viral. So kind of inspired by this example, we're coming up with like how we can make sure that is not actually happening. So how we can have the trained model and kind of detecting whether we have this kind of individual fairness scenarios. And if we do have it, how we can make sure that we can correct the model, or at the decision, we can kind of like give the correct decision. So we have post-processing and in-processing techniques. And in-processing techniques, so for instance, if you assuming that there is a Z1, and for example, this is the space of similarity around this data point, you want to make sure that like all these individuals that are similar to Z1 are included in one kind of like part of decision boundary. Either they should, for example, receive the receive the loan, or they should not, for example, receive the loan. And also at the post-processing time, if we have this, we want to kind of like make sure that we are returning decision based on, for example, if like the space of like this similarity is more towards, for example, rejection, like all the individual, even here, they are getting rejected, et cetera, et cetera. So kind of like making sure that we can guarantee this also at the post-processing. So we kind of like adding this regularizer here and kind of coming up with like the counter examples, like the individual that are kind of similar with our notion of fairness, but receiving the opposite decision, kind of to train the model based on those individuals as well. And we're showing that by this, we can kind of like getting a fair model at the training, but also the performance is not really changing iteration after iteration. We actually now extending this work to causal definitions of fairness. The last kind of like way that people are thinking about like adding fairness to the optimization problem is just thinking of it as a multi-objective optimization problem. I'm not going into much of a detail because my student kind of William is going to talk more about it after with respect to our kidney exchange program scenario. So I will leave it to him to kind of like talk about it. But the way that we are considering this kind of like individual fairness or kind of like fairness notions in kidney exchange program and the utility is that we realize that like we should consider both of them at the same time. We cannot just focus on fairness, and we can actually solve it as this kind of like multi-objective optimization problem that here, if like they are F1 and F2 fairness and utility, then we can kind of like select the parity frontier solution that has the highest distance from the nadir point D, for instance, and the D can be like the worst kind of like scenario for the two of these objectives. And lastly, I want to talk about the techniques that can be used for post-processing. So if you're assuming that, for example, we cannot really we don't have the resources to retrain the models, but we want to, or kind of legally, we have to guarantee fairness. So what we can do is that we can kind of like just focusing at the post-processing step. So here, assuming this is kind of like decision of the model after kind of like training the model, and we have this kind of decision boundary, okay? So this is not the data. I know it's look like about the data processing, but assuming that this is at the post-processing, and this is a decision that like we receive, and we know that, for example, these decisions are not fair. So one approach is that you can actually kind of like find similar individuals that are closer to decision boundary and in favor of like disadvantaged group changing their label. So here you can see that, for example, this individual is very, very similar to the individual who are receiving the loan. So we can kind of like add the kind of like changing the decision of this individual to kind of like be approval. Or we can kind of define different thresholding. So for example, in case of binary classification, we often assume that if the value is more than like the probability of receiving is more than 0.5, then the label is going to be 1. So we can actually kind of learn to have different thresholds for different groups. So for example, for female is going to be 0.4, while for male is 0.7, in order to make sure that the kind of like the distribution is going to be kind of balanced when they are receiving the loan. These kind of approaches of like debiasing either at the data level or at the post-processing level sounds easy, but if you're considering, for example, this kind of like legal aspect that like you cannot really have the sensitive attributes, and this is the case for most of the kind of banking scenarios, we here show that like how can we kind of like having the training model in federated learning without really having access to sensitive attributes to satisfy them in pre-processing and post-processing. And here we are kind of using approaches from multi-party computations and differential privacy. I'm not going in detail of it, but I will be happy to discuss it if you want to get more information. But I just want to show that first of all, it is possible to kind of like not even seeing the sensitive attribute and satisfying it in the model, but this is kind of like a differences between like kind of like doing it at the pre-processing and post-processing. So when we are kind of like doing at the data level, often we have a higher kind of like loss in accuracy compared to the post-processing. But at the post-processing that we have a better performance, you are not really having that much of control on like what you're getting. So if you're starting with a model that is not necessarily having the best utility, you are still going to lose so much of utility here as well. So here I'm just showing kind of like a trade-off between these techniques. So I already showed that like often it is a scenario that you have to combine them. So it's better to kind of like focusing on all of them at the same time, like also cleaning your data, do some sort of in-processing and post-processing. But if you cannot do it, it should be kind of like knowing that like when you're kind of doing it for data level, maybe when you're cleaning it, you can actually reuse it for multiple other applications. It is also kind of more scalable to focus on the data or at the decision because it is more scalable, while models may kind of like requires kind of like more computing power to retrain them or adding the constraint or regularizer to it. All of them are easy to audit because we are kind of like using a fairness notion, but the only approach that you do have this kind of fairness and performance trade-off is when you are looking at the in-processing approaches. So you're just using data or the outcome, you don't have that much of control. And then if you're using kind of like the model, for example, representation learning model, or when you're adding it to the optimization problem, you can guarantee generalization error, right? So like if the distribution are changing a little bit, even if you're kind of like adding constraint to this kind of like optimization problem and guaranteeing 100% for the training model, it doesn't necessarily guarantee at the test time. So what are the takeaways? So I kind of like give you the space of like what you can do with respect to algorithmic fairness. This is a scenario, it's a realistic harms that we are dealing with it. And my kind of like suggestion is that think of like participatory design. So you have the stakeholders, you know, your customers, kind of trying to kind of think about this individuals when you are kind of collecting data, when you are kind of like designing your model and kind of looking at the outcome. Responsible AI also is not just about algorithmic fairness. So as I mentioned, I'm also working at this intersection of fairness and privacy, but also when we are designing this kind of responsible AI model, we should consider explainability of the model, robustness of the model, accountability, et cetera, et cetera. So I will encourage you to educate yourself about it if you have any kind of applications. So trying to focus on your customers, kind of like at least what you can do is kind of like trying to measure the performance of your model at kind of like different subgroups that are among your stakeholders, and trying to make sure that like the performance is kind of similar for all of them. So the experience that they have is going to be similar. Always ask whether the AI is appropriate tool for the task at hand. So AI is not a magic, it's just a tool, and it's not appropriate tool for many tasks. And always consider kind of like which individual or organization are going to use your model, and consider the worst case scenarios. And often bigger is not better. So don't just go for bigger models because they are bigger. In terms of fairness, there are literature after literature showing that like these kind of bigger models, they have more fairness issues. The work that I presented here is the kind of like the works of like my students. So I want to also mention them, acknowledge them, and thank them for all the work that they did in the lab, and also all the agencies that fund my research. So if you have any question, I would be happy to answer, and you can always contact me on Twitter or via email. Thank you so much.
Thank you so much, Golnoosh. We actually do have 2 questions here. So the first one, Gaetan, go ahead.
Thank you very much, Golnoosh, for your presentation. I have a naive question about the Apple case. Can we argue that they should just not consider gender as input of the model to solve the problem? And more generally, when will you recommend to gather information about the sensitive attributes when we want to handle fairness?
So it's a very good question. Thank you for the question. So in terms of that particular notion of like everything exactly the same, the decision should be the same, maybe the scenario is just removing the sensitive attributes to train the model. Yes, that would satisfy that notion of fairness, but in our paper, we actually show that sometimes this kind of like sensitive attributes are helping us in terms of the utility that we can get, right? So we can coming up with this kind of like guaranteeing of the first, so we have it at the post-processing and in processing, and we can guaranteeing it that is satisfying those notions, and we can kind of provide also some sort of flexibility in terms of similarities, not exactly the same attribute, but with some sort of thresholds. Then kind of like including sensitive attributes is actually helping us to have a better performance. But yes, so you can also remove the sensitive attribute to kind of like satisfy that particular notion. But as I said, like sensitive attributes are kind of correlated to non-sensitive attributes. So often this is a scenario that your education level, your salary, like how much time you work in the industry is very much depends on your woman or man, because for example, there is a maternity leave, right? So we do have this kind of dependencies of a sensitive and non-sensitive attributes. So that's why kind of like just simply removing sensitive attributes are not solving the problem. In many kind of like scenarios, even the sensitive attributes, for example, in kidney exchange program that William is going to talk about it, like the sensitivity is actually coming from your characteristic, your blood type level, your compatibility. So it's not kind of like simple to kind of remove those information from the system. You actually need it in order to know who is compatible with whom, but it doesn't necessarily mean that we cannot satisfy that, like, for example, your chance of receiving a kidney should be at least some sort of similar to other individuals because you are needing that kidney and you cannot really control your blood type level, right? So that's kind of like with respect to kind of like removing sensitive attribute or not. In terms of banking, I know there is this question of like how we can collect sensitive attributes. sometimes you even don't have a sensitive attribute. So what's the solution? There are approaches that are talking about, for example, approximation, right? So they're trying to, based on, for example, name of the client or like their interaction, they're trying to predict the sensitive attributes. I'm not necessarily kind of like advocating for those work. The reason is that like when you are training another model for approximating it, you also kind of including another types of biases in your system, which is not necessarily helping you in order to satisfy this kind of fairness notion. So what I kind of like suggesting is that like coming up with this kind of like privacy preserving way of collecting the sensitive attributes like a federated learning scenario that I mentioned, or you can actually kind of like satisfy based on different distributions of the data that you have. So if you are assuming that like kind of transactions of the female applicants and male applicants are different, so you can kind of like set the goal that, for example, your model based on different distributions of the users should have similar decisions. And then without having the sensitive attributes, you can still satisfy it.
Thank you.
Thanks,
Thank
Gaetan, for your question. And thanks, Golnoosh. We'll move on to William now, but thank you so much
Sure.
for the critical work that you're doing in this space. And we look forward to hearing a little bit more about the kidney exchange program. So as Golnoosh mentioned, William Saint-Arnaud is currently completing his PhD at University of Montreal and Mila with a focus on computational logistics.